Welcome, everyone, and thank you for joining us. My name is Marie-Lise, and I will be your host for today's session. This series of short and informative talks showcase cutting-edge research work from ServiceNow AI Research team. The AI Research Bites are open to all, especially those interested in keeping up with the fast-paced AI research community. Today's session features a 15-minute talk from Alexandre Lacoste on GeoBench V2, a next-generation benchmark for Geospatial Foundation Models, and the presentation will be followed by a 10-minute Q&A. Before we begin, let me share a few words about today's speaker. Alexandre Lacoste is a senior staff research scientist leading the UI Assist team here at ServiceNow AI Research. He holds a PhD in theoretical machine learning from Université Laval. He is also a founding member of Climate Change AI and an author of the seminal paper Tackling Climate Change with Machine Learning. With that, it's my pleasure to hand it over to our amazing speaker. Up to you, Alexandre.
Thank you so much, Maryse. Exactly. So today I'm going to talk about foundation model for Earth observations, it's a forward-looking talk towards achieving this. It's a AI Alliance project in collaboration with IBM. Great. But before we start, I must announce that there's some opinions and assumptions as it is a research project throughout this talk. So I've been asking myself the question often, what if we can make a model that knows the Earth the same way GPT knows the internet? Or more importantly, why haven't we achieved this yet? Is it because it's a much harder problem? Is it because there's not enough open data or simply not enough incentive? But first, let's talk about what is a foundation model for EO, Earth observation? What are the expected capabilities? So very much like a VLM, visual language model, you have varieties of input that can go in and variety of output. But what's specific about Earth observation is that satellites are equipped with variety of sensors that goes way beyond just RGB channel of typical images. So you can have multispectral images that can have up to 13, 15 color bands. You can even have hyperspectral, and can have hundreds of bands. You can have radar that can have a different perspective on the data. You can have elevation map. So all of this new kind of data goes beyond what current VLMs are able to perceive, and we have to adapt and understand how to digest this. Also, like I said, like can come around the Earth and revisit the same region, creating a temporal series with different time lag. We have to be able to handle this, and of course, we expect that these models would understand our language and be able to take a large amount of data as input. In terms of output, what's special is that in the domain of Earth observation, we usually expect that the model is going to be able to produce a pixel-wise mask for each pixel, being able to segment or identify some property at each step. And also being able to produce perhaps object detection. This would be typically like text generation, but it needs to be very calibrated such that it aligns well on the pixels of the image. Forecasting and being able to reason and produce report would also be fundamental. So at the moment, there's no such model being able to handle well all of these capabilities. Usually a subset of these, but what could we do if we have that? So let's imagine which kind of tool we can build on top of this. Pretty much like ChatGPT, you can have, if your model is capable of zero shot, you could put data sets that you accumulated from your remote sensing, perhaps image or drones, and you could chat and interact and learn about your data. It can identify things that you didn't realize it was there. It can count objects. It can make a report. So this would be an important tool that is starting. We already have some tools like that, but perhaps the most standard tool here is still having the ecosystem of fine-tuning. The downstream application are still very focusing on starting with a model, gathering some data, and fine-tuning to deliver accurate and top performance on. So we still need to consider this kind of approach. And something that's very new this year with the agentic era is agentic models, agents working with foundation model that can use it as a tool to understand some element. And that unlocks very interesting application. For example, you can have your agent producing a report based on, I don't know, like drones collecting new data on your city, and perhaps detects its occlusion at a specific region, and so it creates uncertainty, and it can identify that and perhaps contact through an API or through email the people responsible for gathering more email, perhaps remote sensing people, companies, and you get more data for this specific region, and automatically you can integrate that the next day in your report generation. Very much looking forward for such kind of tool. Now, there's no reason to do any of this if we don't talk about downstream application. This is where the value goes. And so I'm going to glance over the different category. Disaster response is perhaps the field that's going to see biggest improvement in the coming years with zero-shot model and agents, where let's say you have an earthquake or an event that just happened, and you want to be able to deploy the proper resources or develop a plan for that accordingly. So you have drones or satellite providers giving you new imaging, can rapidly analyze this. And this is fundamentally different than having to fine-tune your model specifically for a given task. Agriculture and food security, very important one. On the farmer side, I think they're going to benefit more from precision agriculture. So where it's going to be more useful is for policymakers in agriculture, being able to have an holistic understanding and yield forecasting, information that farmers are not necessarily sharing, and being able to develop better policies and enforce better policies can create overall better teamwork with agriculture. Perhaps my favorite here, the carbon and biomass accounting. If we have model that can sense the earth in a more precise way and be able to understand where the carbon cycle goes, and we can develop a better carbon economy instead of just giving money to some people so they don't cut trees. At least we can monitor the forest more precisely and know if this forest is progressing accordingly. Of course, other important city planning and defense and intelligence is also benefiting from any progress we do in that field. If we look at a high level, we have talked about capabilities, tools, and downstream application. This gives an interesting perspective of the field. But what we're going to focus on here is how do we ensure that progress is going to benefit downstream application. That's going to go through benchmark. So benchmarking, if done correctly, it helps the community move together, and it guides the direction and improves the quality of the science. This is really what we're trying to achieve by developing better benchmark. So we're going to first talk about benchmark in the category of fine-tuning. It makes it much harder to evaluate because we want to know if a base model that you developed is going to be good after you fine-tune it on a data set. So that means that you need to fine-tune it on multiple different data sets, and every time the fine-tuning, you require training, and there's a validation, like cross-validation of a hyperparameter. Can be a little tedious and it's hard to develop. But despite this, the community is providing a variety of benchmark in that field. And all of these benchmarks are composed of multiple data sets. Some of them are a little bit more precise. For example, FOMO-bench and REO-bench, they're focusing on forestry monitoring, and REO, it's on robustness to noise. So the scope is a little bit narrowed down, but the other benchmark, they are trying to address a wide range of capabilities. So in that perspective, I also created a column for each of the capability that we've been discussing, and I was curious to know, are these benchmark evaluating these capability? And we see that segmentation is very, very present in the community, but some of them are underrepresented. Temporality, measuring there's not that many data set or that many benchmark focusing on is your model good at integrating multiple image at the same location. Still there, but it's not as present as we would like. And We talked about large context and forecasting. Uh, while these fields exist outside of that community, they are very underrepresented or not measured in any of these benchmarks. Yeah, so this represents a blind spot of our community. Another important aspect is the notion of open license. So all of these data sets, they are open, the benchmark contain data set are open license, but some of them have a non-commercial. It can be a Creative Commons -NC. So what that means is that it's hard to have research and industry collaborating together. If you have a new model, you cannot, if it's a startup or a company developing a new model, you cannot safely evaluate it on these benchmarks. So that's an issue. So on the other benchmark here, so a couple of years ago, I worked on GeoBench and made sure that they were all open license data set. And but there was a limited set of capabilities. It was not full coverage of what we would expect. So lately, we worked together with AI Alliance and IBM, and we developed a new version of the benchmark, GeoBench 2, to increase the scope, to address more capabilities and having a leaderboard and aggregated metric. So let's talk about GeoBench 2 a little bit. So it's about, again, evaluating fine-tuning from a frozen back or using a frozen backbone. We have 19 data sets inside the benchmark. And all of these data sets, they are original data set that were developed for remote sensing, but we downsampled them to be able to do faster evaluation. We made sure they were discriminative and challenging tasks by discarding the data sets that were not very challenging. After evaluating on them, you can just discard them. So all of these 19 data sets, we grouped them into 9 different subsets. And all of these subsets, they represent the capability that we've discussed earlier. So we want to be able to know if a model is having it and the capability that you care about. You need to evaluate that on more than one data set to be able to have like statistics. Is it consistent? Is there uncertainty, like reduce the uncertainty to be able to say something about your model? So having at least 4 data sets per capability is important. And having different perspectives. So on your base model is also important. So this was the central part of GeoBench, being able to have this multiple capability evaluation. And like we discussed, it's all fully open license, and we have a leaderboard. Now, at a glance, if we look at the results that we get, we evaluated on this benchmark 14 different models, and we ranked them according to the main, so what we call a core here is like it's a representative subset of the whole benchmark. And if we rank them here according to that first capability, and we look at all the other ones, we see that it's jumping all over the place. And what this tells us is that there's no model at the moment that are like dominating all the other model. So there's every time you look at a different perspective, you gain information about, okay, well, maybe this model is better at this, and then you can investigate why it is better. And what we have is that Clay and Confnex, they are overall better. Here, they're the 2 tops. But we have the Terramine, the clear winner in multispectral. Here we have like model like really hanging out, standing out into some of the capabilities. This is very interesting to learn from us. But also, most interestingly, Confnex is not even a foundation model for Earth. It's just trained on image, and then it was trained on image and then adapted. So the architectural decisions and the size of the data sets, and it's the extra large one, were a key component delivering the performance. Of course, zero-shot evaluation is much simpler and also very important. It's more like in the case where you want to have like a ChatGPT-like interaction. I'm just not going to dive into that, but at a glance, there's already a couple of benchmark existing in that perspective. And again, we have multi-temporal that's really underrepresented, and large context and forecasting that are not represented, and very few leaderboard. Our community is not a big fan of leaderboard, apparently. So I'm going to point to GeoBench VLM. This is also collaboration between ServiceNow and IBM, and also MBZ UAI. But I'm not going to dive into that. Quickly, since the time is running, I'm going to talk about one potential research axis. But yeah, if you have questions, there's many more that we can discuss. And this is one of the core challenge is sensor fusion. So if you have multiple kind of inputs, and they may not be all present at the same time, and you have temporality, you can have multiple revisits, or maybe you have only one. So this can be very hard to encode, especially if you work with convnex or older convolution method where you require a dense array. But if you work with transformer-like setup, it's encoding a set. So you can work with a set of anything as long as you put the proper encodings. So all the different meta information that you have about which kind of sensor, which kind of bands or temporality, you can put that into spatial encoding, temporal, which kind of sensor it is. So you create an encoding and then you patch all of these and you send that to a transformer and it's able to digest all of that very naturally. You can use a mask autoencoder by masking this, and this is what a lot of people do in the literature. It comes at a very specific drawback. So this is a typical example that you get in remote sensing, where you have an image and you're often limited by the resolution of your image. Here, it's a crop where we have cows. They are all happily eating grass. And the issue is that with the pixel that we have, they make like, what, 3 pixels by 4 pixels, really, really hard to detect. And if you just send that to a VIT, that's going to break that into 16 by 16 patches, then you lose all the low-level information that's really important. Like a patch would contain 2 to 4 cows, or sometimes 0. So this is a big trade-off that you get in that situation. So it's a VID and MA. They're good at centrifuges, but they cannot get fine-grained details. As both convex and Swin architecture, for example, they work well with fine grain, but they cannot do centrifusion elegantly. So, what would be the right way to move forward? Do we want to have some kind of hybrid architecture? Do we want to start working on a new kind of architecture? This is a big open questions where we can work on. And that's going to be it for today. And I would like to leave room for questions if you have any.